So now what happens when we displace these links in this Ackermann steering mechanism? Okay, so that is what we are going to look at, right. Then we will see how they are displaced. Okay, so we are going from the ground up, right, then we will go till the steering wheel, okay, as we slowly look at the entire steering system. So let us consider what is typically called as the Ackermann steering condition. So let us look at the schematic. So let us say that this is a simple schematic which essentially explains what we are going to discuss, okay, based on, okay. So suppose let us say we had a mechanism like this and we want to achieve this, right. What do we want to achieve? We want to, when the steering wheels are turned by using this mechanism, we want to achieve what is shown in this figure, right. So the axis of the two steered wheels should intersect the extended rear axle center line at the same point. So that is our requirement, right. Suppose if we were to achieve that, then what should be the constraint or the condition, right. So based on what has been proposed by Ackermann. So that is what is called as Ackermann steering condition. So let us discuss this. So let us say, you know, like we consider this what to say simple schematic where we have a vehicle of wheelbase L. So we already know that capital L is wheelbase and our CG is at a distance of L1 and L2 from the front and the rear wheel centers. This W is what is called as a track, it is not the vehicle width, okay, although people interchangeably sometimes use it with width, right. So it is what is called as a track of the vehicle, right, and we can see that without loss of generality, let us assume that we are taking a turn to the left as far as this figure is concerned. So this delta I is the inner wheel steering angle and delta O is the outer wheel steering angle, okay. So we draw lines which are perpendicular to the axis of the wheel plane, that is along the axis of the wheels and which are perpendicular to the wheel planes. Then let us say those lines intersect at the same point with the line projected from the rear axle axis, right. So let us say that is O, as we know this is the instantaneous center of turn, right, and we draw a line segment from the instantaneous center of turn to the vehicle center of gravity. We get the turning radius which is denoted by capital R, right. Now we can immediately observe that this angle is also delta I. Why? Because the two line segments are mutually perpendicular to the other two line segments, right. So essentially we know that the included angle between two mutually perpendicular sets of line segments is going to be the same, right. So that is what this angle is delta I. Similarly the angle made by the line segment OB with OC is also going to be delta O, pretty straightforward, right. So that comes from basic geometry, okay. So let us say we call this distance as R1. What is this distance R1? R1 is the distance from O to the longitudinal axis of the vehicle, the central longitudinal axis of the vehicle, okay. So these are the various parameters. So now let us see what happens with the Ackermann steering condition. So let us say we consider the triangle OAC, right. So if I consider the triangle OAC, what will be tan of delta I? It is going to be equal to L divided by, of course to begin with it is going to be AC by OC, right. So AC is going to be the wheelbase L, OC is going to be, as we can see, it is going to be R1 minus W by 2, right. So we subtract W by 2 from R1, we get OC, right. So this will give us that cot delta I is going to be equal to R1 minus W by 2 divided by L, right. So let us say we call this some equation 1. So, similarly, let us consider triangle OBD. Okay. So, if we consider this triangle, we can immediately observe that tan of delta O is going to be equal to BD by OD, right. BD is once again going to be L, OD is now R1 plus W by 2. So, this will give us cot delta O is going to be equal to R1 plus W by 2 divided by L. Let us say we call this as equation number 2, alright. So, now let us say we subtract, okay, equation 2 and equation 1. So, what do we get? We are going to get cot delta O minus cot delta I, that is going to be equal to W by L, right. So, that is what we are going to get. So, this condition, this equation is what is called as the Ackermann steering condition. Okay. So, this is the Ackermann steering condition, right. So, what does this condition tell us? Suppose if you are given a vehicle of track W and a wheelbase of L, if we want to achieve, like what was expected, that is like the axis of the two steered wheels should intersect at the same point with the rear axle axis, then we should have this equation to be satisfied. So, what does this equation tell us, like convey? It gives us a relationship or a constraint between delta naught and delta I, right, that is what is important. So, the steering mechanism has to be designed in such a way that given delta I, delta naught should be related by this equation, or given delta naught, delta I should be decided based on this equation. So, that is the significance of this equation. So, in essence, this provides a constraint on delta naught and delta I given a fixed W and L, right. So, that is one way to look at this Ackermann steering condition, right, is it known, okay. So, now if we continue and we add equations 1 and 2. So, instead of subtracting 2 and 1, let us say we add 1 and 2, what are we going to get? We are going to get cot delta naught plus cot delta I, that is going to be equal to 2 R1 by L. So, this implies that R1 is going to be equal to L cot delta I plus cot delta naught divided by 2L, 2, right, correct, that is about. So, why is this important? Thus, the turning radius, see we can observe that the turning radius R, I can use this right triangle, right, R squared is going to be L2 squared plus R1 squared, right. So, using the Pythagoras theorem, okay. So, thus the turning radius R is, if you take R as a square root of L2 squared plus R1 squared, this we all get it as L2 squared plus L squared times cot delta I plus cot delta naught whole square divided by 4, right. So, this will be the expression for the turning radius, right. So, we can immediately see that the turning radius obviously depends on how much the steered wheels are steered, right, so obviously, right. So, that is it, okay. So, this is the Ackermann steering condition. So, this is what we ideally want, that is if you want to turn the steered wheels to achieve whatever we have already seen in the schematics, right. Now, question is that like how does one achieve it, or in other words what happens with the actual mechanisms that one has, right. So, let us look at that. So, the question, the relevant question to ask is that how can one realize this condition, right. Is it achievable perfectly every time, or is there some trade off, right. So, for this let us look at a trapezoidal steering mechanism. Okay, so let us look at a trapezoidal steering mechanism, and then like let us look at how well this is achievable. So, let us consider a simple schematic, this trapezoidal steering mechanism. Okay, let me put it here and let us expand it. Oops. I don't think I will have space. All right. So, let us say, as the name indicates, you know, like the steering mechanism is in the form of a trapezoid, right. So, let us say, you know, like looking at this diagram. So, let us say this is the solid axle to begin with, right. So, this is the track rod, okay, and this angle, this is the track, vehicle track, you know, W. This angle is typically represented by beta, okay. So, that is the angle between the wheel plane, the wheel central plane, and the what to say, the rod connecting the track rod on the to the kingpin, right. So, this is typically denoted by D. People call this as the offset arm length, right. So, this is essentially denoted by D as far as this trapezoidal steering geometry is concerned, you know, this is what is called as the offset arm length, okay. So, if you look at this trapezoidal steering mechanism, the two main parameters are D and beta, right. So, those are the two important parameters, right, as far as a trapezoidal steering mechanism is concerned. Now, the question is that how do we choose D and beta such that that Ackermann steering condition is satisfied. See, what do we want? We want to have a steering which will satisfy that Ackermann steering condition, right. So, let us look at the displaced steering linkage, right. So, let us say I turn my steering wheel, and let us say this the schematic at the bottom is the what to say, the displaced condition, right, and we can see that the inner wheel is turned by an angle delta I, right, and the outer wheel is turned by an angle delta O. This angle beta between the central wheel plane and the tie rod, right, remains the same, okay, that is the steering arm, right. So, it is going to pivot about the kingpin or the ball joint, but they are going to rotate, and so the relative angle between the central wheel plane and the steering arm, the tie rod assembly, is going to remain beta. That is what we can see in this figure. So, of course, this is exaggerated, so just to convey the point, right. So, let us say, you know, like this by this is the displaced configuration. So, now we see that we can trace out a right angle triangle XYZ, right, in this bottom figure. So, immediately we can observe and we can write down using the Pythagoras theorem that xy squared plus yz squared is going to be equal to xz squared, right. So, that all of us can immediately observe, right, from the triangle XYZ. Now what can we say about the 3 lengths? Okay. So let us say first let us go from xz. So what do you think xz is going to be? See, xz is going to be the length of the this track rod that we can obtain from the above figure, alright. And what is that going to be in terms of w, d and beta? We can immediately observe that this is going to be w minus 2d sin beta, right, because why? This is going to be d sin beta, do you agree? So this entire length is w, so you subtract 2 times d sin beta, so you get xz. Now what about xy? Xy is going to be this distance, right, is it not, correct? Now we can project it into 3 parts. So xy is going to be this distance minus this distance, do you agree? What is the bigger distance? You can immediately observe that I can rewrite as d cos delta naught minus beta, right, where do I get it from? It is from here, it is this distance, right. So because this angle is going to be, we are going to get d cos delta naught minus beta, because delta naught is going to be this angle, sorry, no, this entire angle is going to be delta naught. So this angle, the smaller angle is going to be delta naught minus beta, right, do you agree? So and this length is anyway d, so what is this distance? This is going to be what we wrote down, right, d cos delta naught minus beta. Now this distance, smaller distance, is going to be d cos delta I plus beta, correct, do you agree? That is what this is. Now what about yz? Yz I can rewrite in 3 components. First is this component, right, plus this component, right, minus this component, correct. What is the first component? This is w, right. Then what is this component? This is going to be d sin delta naught minus beta, right, that is the opposite side in that right angle triangle. So that is going to be d sin delta naught minus beta minus d sin delta I plus beta. So this essentially gives us this condition for the trapezoidal steering mechanism. So I will quickly explain what this means once I write down this expression. So we have d cos delta naught minus beta minus d cos delta I plus beta whole square plus w plus d sin delta naught minus beta minus d sin delta I plus beta whole square is equal to w minus 2d sin beta whole square. So this is the expression that we get. So what does this expression give us? It gives us a relationship between delta naught delta I and d and beta and w and for the trapezoidal steering mechanism, okay. So we will revisit this expression tomorrow, and then we will discuss whether such a steering mechanism will indeed meet the Ackermann steering condition, okay. So we will continue this discussion in the next class. Thank you.